welcome to the Late Night Talk Show. I'm your host Anushree, and we are filming this at 4 p.m., so it's not really late at night, but we're never too late to learn, allegedly. Tonight's episode features your passwords, your bank accounts, your entire digital life potentially at risk. Not by hackers, not by a data breach, but by physics. So we brought in some of the brightest minds I know to explain what's going on here. So if you two could introduce yourself real quick.
Yeah, I'm not sure I'm the brightest mind. I don't know like the quality of the minds you know if I'm the brightest mind you know, but I'm just joking. So, hi, I'm Sean Witt. I'm a math major here at Purdue, and I love cryptography.
Hi, my name is Sean. I am a pharmacy majoring in Purdue, and I am here for policy.
We also have a special guest later in the show, so stay tuned. So let's start from the top. So everyone uses the internet, everyone's heard of encryption, so what exactly is it?
Yeah, so at its core, the math behind encryption, behind the safety of our emails and so on, it's relatively simple. It's called the RSA algorithm. So what you have is you randomly choose 4 numbers, 2 primes and a public key and a private key. The public key locks away the information like a padlock, and the only way you can open with the padlock is the private key. Now, it relies on the fact that mathematically multiplying the 2 primes is very easy compared to how computationally intensive it is to factor the primes factor the products back into its prime factors. Essentially, it would take more than the age of the observable universe if we do it classically. So this is what is protecting your emails, your passwords, and the entirety safety of the internet.
Longer than the age of the universe. Wait, that sounds pretty safe.
Yeah, it used to be, but now with a certain thing called quantum computing, maybe you've heard of it, it's not really as much anymore.
Okay, that's really not comforting, but that's also your cue to explain why, because I'm not the expert here.
But that's why we have a special guest. Glad to have you on.
Now, here's where things get fun. Classical computers, everything we've ever done, right, it works in bits. A bit is a 1 or a 0, an on and off switch. So your laptop is essentially just billions of very fast light switches. But a quantum computer, on the other hand, uses qubits, aptly named. Now, because qubits are so small, they work on the realm of quantum mechanics, and not in the realm of regular old Newtonian mechanics, right? So it can be a 1 and a 0, actually, at the same time. It doesn't just have to be a 1 or a 0. So, and this is called quantum superposition, right? It exists as both 1 and 0 until you measure it, where the state collapses, and essentially it has to choose. Now, mathematically, a qubit is a unit vector in the set of complex numbers, written in Brockhead or Dirac notation, because it's in the set of complex numbers, as something like alpha times a 0 vector plus beta times the 1 vector, right? Where alpha and beta are coefficients whose squared sum adds up to 1, of course. Now, with n qubits, you're spanning a space of 2 to the n dimension simultaneously. So with 300 qubits, that's a Hilbert space with a dimension of a size that is literally larger than the atoms in the observable universe. So, that's where the power is. Yeah. Now, Shor's algorithm, which was written in 1997 in a paper, according to this paper, right, if you superimpose all of these possible inputs simultaneously, the algorithm cracks RSA encryption at polynomial time. But it's not directly factoring the number, right? Instead, we're actually transforming factoring into a period finding problem. Period as in a wave, right? It creates a superposition of all possible inputs x, computes a to the x mod n for all of them at once, and ends up with a pattern that repeats a hidden periodic structure. Okay, so a quantum algorithm is carefully designed so that these amplitudes, these coefficients, alpha, beta, interfere with each other like waves, and so some waves add together, right? That's constructive interference, and some waves cancel out. That's destructive interference. So the algorithm is able to manipulate the system so that the wrong answers cancel themselves out, and the right answers are able to reinforce each other, so that by the time you measure the system, where you force the bits to choose a state, right, the probability of seeing the correct answer is very high, and the wrong answers nearly 0. So classically, finding the period is the hard part. That takes forever. But in quantum mechanics, you just superimpose all possible inputs simultaneously, and the algorithm can extract the period in polynomial time. And in plain English, right, what takes a classical computer longer than the universe has existed, a quantum computer running Shor algorithm does very fast, comparably. I hope that made sense to everyone. That's all from me, though, for tonight, so I'll pass it back on to the talk show host. Thank you.
Really hope something's doing about this, and I think you would know a lot better about it. So do you want to talk about policy for a second?
Government is already started the transition. The main effort is called the post-quantum cryptography, or PQC. Instead of relying on discrete numbers, this is a new system that use the math problems that are they cannot be easily solved by even for quantum computers. Something like lattice-based cryptography.
So these safeguards and the protections, all of that already exist. So why isn't anyone using them?
Having the solution doesn't mean that we can change everything right away. Migrating the internet cryptographic infrastructure is massive. Every device, every server, and even every protocol should be integrated. There are also some risks. Some of the new algorithms take longer keys or require more computing power, which can slow down the server or even break the whole compatibility. So organizations have to take extra attention for this, and that's why NIST is suggesting the gradual migration before they face the urgent situation.
So as we all kind of summarized pretty well, I'd say. So that's all for the late night talk show that's happening at 4 p.m. And I hope you tune in for our next episode, which is kind of fictional because this is a group presentation that's never happening again. But we'll see you later. Bye bye.